First thing I'm going to talk about is what's up here. Now, there's a PowerPoint presentation in your notes, and it says Logistic Regression Options for Assessing Confounding. Okay. Now, what we've done, what I did in the last class, was I talked about the modeling strategy, the 3 steps for the modeling strategy: variable specification, interaction assessment, confounding followed by precision. And I illustrated that using the M Rsa example. And I illustrated that in 2 ways. One is I used the example in the data itself where we had a single exposure and we had the exposure was previous hospitalization, the outcome was MRSA status, and there were 3 variables to control for: age, gender, and PAMU, previous antimicrobial use. And we went through the process with this example, and we saw that if we looked at a table like this table, we were able to make a decision, or at least a couple of choices, about what the best model was. And the best model was either what I refer to as the gold standard model. And this is a model that doesn't have any interaction terms in it. There was no interaction. Why was that? Why was there no interaction? Because when we evaluated interaction, when I described it last time, we found that none of the interaction terms needed to stay in the model. So we can get rid of them and start with a no interaction model that has the exposure variable and starts off with these 3 variables that we're interested in controlling for. And then what I did was show you how you could find the best model by what you then have to do is assess confounding and also consider precision in deciding whether you can drop one or more of these 3 variables: age, gender, or PAMU. And the way I considered confounding is I looked at the odds ratio for all possible subsets of these 3 variables, and I looked at to see which odds ratio, which if any odds ratios are within 10% of the gold standard odds ratio. The gold standard odds ratio was the one that controlled for everything, the 3 variables we started off with, or after interaction. And we only found one subset of these 3 variables that gave you essentially the same answer, at least within 10%. And then we looked at the confidence interval around the odds ratio for that subset and compared it to the confidence interval for the gold standard. And we asked the question whether we gain precision by dropping the gender variable, which we'd be dropping to get this particular subset. The gender variable is dropped. And we found that we gained a little bit of precision, but not a lot. So the answer in terms of what's the best model, either one of these 2 models is essentially saying the same thing. They're essentially giving you the same odds ratio and essentially the same amount of precision, and the odds ratio is significant. Because the confidence interval doesn't contain 1, we could also look at and do a test for it using the logistic model that we have in SAS, the logistic program that we have in SAS. So this is what I refer to as the all possible subsets approach. Because when we consider the 3 variables that we wanted to consider for control, we didn't know whether we wanted to control for all of them or drop some of them. We considered every possible subset to compare it to the gold standard. And this is sort of the best way you can deal with confounding if you have a bunch of variables to control for, by considering every possible option that you have for comparing it to the gold standard and making some kind of reasonable decision according to the guidelines I've been showing you about how you assess confounding and how you consider precision. Okay. Now, there's a problem with this. There's a sort of, you might say, a technical problem, is that if instead of having 3 variables here that I wanted to control for, I had 10 variables I wanted to control for. Instead of 3, I had 10. And I wanted to consider the all possible subsets approach. Okay? Think about that. How many subsets are there? A lot. That's one way to say it. I mean, mathematically, to figure out all controlling for all 10, any 9, any 8, all possible subsets. So if you wanted to use that approach, which is still the best approach, you'd have a much bigger table you'd have to deal with. And you'd have more work to do that. It's not that you couldn't do that, because the computer's doing most of the work for you, because the computer's fitting the model. So you could specify to the computer, fit all possible subsets, but you'd have to write every possible subset and then put it in a table like this and go through the same process. So, but you wonder when you think about this, is there a way I can do something like all possible subsets and shorten the process and still get a good answer? Is there a shortcut? That's what I'm saying. And so I want to talk about two shortcuts, two possible shortcuts. And either of these neither of these shortcuts is as good as doing all possible subsets, because that's allowing you to see everything. But I want to illustrate these other two shortcuts. And that's what I'm going to do first here today. So we've talked about the all possible subsets approach, and we just saw that, and I just said there were only two models, the gold standard model and the one that dropped that dropped gender, gave you the same odds ratio and essentially the same confidence interval. And by the way, when you want to compare confidence intervals and look at precision, the usual way you do that when you're doing a nonlinear model is to not do the confidence interval width, but the confidence interval ratio. But in either case, you see that there's a little gain in precision when you drop gender, because either the width or the ratio for this reduced model is a little less than the width or the ratio for the gold standard model. You follow me? You with me on that? You follow what I'm saying? Okay, so now let's look at the second, another alternative, a shortcut. Okay, shortcut way of doing it. Again, it's not the best thing, but it's a way you can, skip all possible subsets, okay? This is what I recall, and by the way, in the book Logistic Regression, the self-learning text, it's not written in there. The thing was written up and used, but it wasn't actually put in the third edition. So what you're seeing now is something that I don't believe is in the third edition, so you're seeing it here, and it's in your notes here, and I want to talk about this because this is something to talk about, although again, as I say, the all possible subsets approach is better. But let's talk about this, the standard backwards elimination approach. Now suppose, for example, instead of having three V variables or C variables that you wanted to control for, say you have several of them, and I'm saying suppose you have P Vs, P could be 10. Okay, what does this approach say? It says drop the least, it's really going backwards elimination with these V's, is what it's saying, which means you drop the least significant V in terms of what you might say the 0.05 level if you want, the V variable from the gold standard model, and rerun the model until you can't drop anymore. That's backward elimination, okay? Now, what's wrong with that? How would you criticize that in terms of what I just described? What are we assessing here? What are we trying to drop? We're trying to drop V variables. What kind of variables are they? Potential confounders. What are we doing if we do this method that I just described, the way I just described? What are we doing? We're doing statistical testing to decide how to drop them. Well, that's not right. Right? Statistical testing doesn't assess confounding. So there's something that's not exactly, I don't know what the right word is, correct about that. But we would get rid of some variables that way. But we're not getting rid of the variables because they're not confounders. We're sort of getting rid of them in a sense. We're ridding the ones that are not significant. And when you think about a variable that's not significant, if you think about how you learned about significance or modeling, and the first time you ever had linear modeling, you're talking about if a variable's not significant, it's not explaining a lot of variance. Have you heard that expression? So if it's not explaining a lot of variance, you might say it's not contributing a lot to precision. So if you drop a variable by testing, you're sort of saying that in an indirect way. You're not looking at the confidence interval, but you're saying using testing, somehow if I drop this variable, it's not very significant, it's not explaining a lot of variation, it's not contributing to precision. So in a way, this approach, the backward change in estimate approach, is a way of evaluating precision with the variables that are in the model, although it's not dealing with confounding. Okay, so now what I say here is, and by the way, this can be used even if there's interaction, but I'm illustrating it for no interaction. You can even do this for interaction. If there's interaction, the only variables you can consider dropping are the ones that are not part of product terms that have to stay in the model. Now, we're not done yet, because the problem is, let's say you started with 10 V's and you went backwards and you were able to drop 8 of them. So there are 2 left. But once you got to the 2, let's make it simple. Suppose the 2 that are left are V1 and V2. They're left. And you've got now in your model E, V1 and V2, and you've dropped the other 8 of the 10. Okay, you've gone backwards to backward elimination, considering in some sense precision by dropping a bunch of variables that they're not sort of contributing to precision. But what have you done about confounding? Nothing. Well, how could you deal with confounding at that point? You now have a model that has E and 2 V's, not 10 V's. And you want to see if that model is going to control for confounding. How would you do that? Remember, it's a no interaction model. And for this no interaction model that just has 2 V's in there, what's the odds ratio for that model? It's e to the beta, where beta is the coefficient of the exposure variable. Okay, that's the odds ratio. What's the odds ratio for the model that we started off with, which had all 10 in there? It's also e to the beta. Are the 2 e to the betas the same? Well, they might be. They might be and they might not be. Well, what if it turns out you go backwards and you're not doing all possible subsets? You're just doing it one step at a time until you get down to only 8 steps, say. And you're getting down to these 2 variables. And when you evaluate e to the beta for the model that's left, you find that it's within 10% of the e to the beta for the model that you started off with. What does that tell you? That tells you that model controls for confounding. So you've now found the model that you've sort of hoped that has considered precision to get to that model, but now you've found a model that's controlling for confounding. That's a way of shortcutting the process rather than doing all possible subsets. You got the idea? That's a shortcut process. It's not as good as all possible subsets because it might miss something. But there's a problem with what I said. What if you compute e to the beta for the reduced model, and the e to the beta for the reduced model is more than 10% from the gold standard e to the beta? What would you be tempted to do? Well, you start adding things back in that dropped out, right? So you add the last one to drop out prior to where you got, and then you look at e to the beta for that model. And if the e to the beta for that model is within 10% of the gold standard, then you're sort of done. You've got a model that's sort of considering precision and also considering confounding. So that's how you do it. You keep adding things back until you may wind up having to add everything back. Okay? But that's this method. Okay? And it turns out that if you use this method for the MRSA data, you actually get a different answer than you would when I did when I described the all possible subsets answer. In fact, so what I'm saying here is that there's a third step. Compare the odds ratio in the model resulting from the backward elimination to the gold standard odds ratio and see if the e to the beta obtained from BWE is within 10% of the odds ratio. That's what you'd have to do, and if it's not, then you start adding things back. If it's not within 10%, add non-significant V's back until the 10% rule is satisfied. That's what I'm saying. And if it's within 10%, stop. That's what I'm saying. Does that seem to make somebody had a question? There you go. Okay. Who are you? What? Anna Newt Levinson. Okay. You related to Richard Levinson? Everyone asks me that. I knew. Somebody had to do that. Way back in at the beginning of time. Okay.
So when you start adding your V's back into the model, are
yes.
you essentially just going in the order that you would have taken them out of? So
yeah, that's what I'm saying. What makes sense, the way you do it in the order that you took them out, because then you're sort of considering what you've done to get rid of variables in terms of precision. So that's all I'm saying. And that's a reasonable way of doing things, you know, although it's not guaranteed to give you the same answer as the gold standard model. And in fact, let me show you something. Now, here's the output for this model, the gold standard model. The output for previous hospitalization, age, gender, and PAMU. Okay? And look at the last column where it gives you p-values. The last column is p-values, right? Now you notice that the three p-values, the last three p-values, are the ones you want to look at, right? Aren't they the ones you want to look at? Because therefore, whether or not you can drop any one of the three, you're keeping the E variable in the model. So you're not touching previous hospitalization. But you notice that for these three, what do you notice? What's the least significant p-value? The one that corresponds to the gender variable, right? Correct? Is it significant? It's significant. So what does that mean if I was using this method, this approach? This would mean that since the least significant is significant, I can't drop it. So using the backward change, not the backward estimate, backward elimination approach, I keep the gold standard model. I don't drop anything. That's what this says, okay? Which is a different answer than what you would get if you did the all possible subsets approach. So I'm telling you, you don't necessarily get the same answer. Turns out now, notice that these p-values are p-values you get when you use the Wald test. These are all the Wald tests, right? There's another test. It's called the likelihood ratio test, right? And we talked about how that's better than it's better because it has better statistical properties and everything. So it's not guaranteed to give you the same conclusions as the Wald test. But it turns out that if you actually do the likelihood ratio test for all three of these things, given the rest in the model, you will find out that the least significant likelihood ratio test has to do with the one for gender, same one. And you'll also find out that it's also significant. So you would find, whether you do the Wald test or the likelihood ratio test, that you can't drop the gender variable. That's what I'm saying, okay? So that's an alternative. It doesn't give you the same answer. It might not, okay? Now, what's interesting about this, I don't know if it's interesting. Who knows what's interesting to you guys, right? Football scores? No, I don't know, you know. That's not interesting to many of you, so anyhow. But look at this, is that if I actually get the confidence interval, if I don't look at the Wald test or the likelihood ratio test, I look at the confidence interval around the odds ratio for the effect of exposure, which is the previous hospitalization variable. I'm not looking at the test statistics for the three variables I'm evaluating whether they should stay in the model. Look at these two confidence intervals. In fact, you've already seen these. We just showed you before when we were doing the all possible subsets. What do you notice? What do you notice? Is that even though it turned out when you did the testing, you had to you actually looked like you gained precision or you explain variance by adding or having gender in the model. It turns out by dropping gender and you look at the confidence intervals, you actually gain precision by dropping gender. So you get can you see that? This is less precision than that, okay? And yet the tests seem to imply that you gain precision when you kept gender in the model or added gender to the model that didn't have it, okay? So that tells you that, well, you know, doing these tests isn't the same thing as looking at confidence intervals. It's not exactly the same thing. So that's a reason to worry a little bit about the testing approach, this BWE approach, that you might say it's better to do tests, but this is something that, again, it's a shortcut. It may help you get a better answer. Rachel has a question? No, you're just going like, whatever, okay. So I'm saying model with gender has slightly better precision than the gold standard model, even though gender significantly adds to the prediction of MRSA from the BWE testing, the backward elimination testing. You're getting a contrary answer. So all I'm saying is that this approach is sort of a little debatable. You might, but it's an approach that you can take. It shortcuts the process. best approaches. Now, there's another approach. It's called the change in estimate approach. Change in estimate backward elimination approach, a different approach. Okay, so I want to talk about that. That's one a lot of people like better, even though it's not as good as the all possible subsets approach. Okay, I want to talk a little bit about that. Okay, so what it says is, considering the again, we're talking about the M Rsa data set, although we're talking about it more generally. The M Rsa data set had 3 V variables, right? Age, gender, PAMU. And considering the V variables one at a time, drop the least confounding, using the 10% rule, V variable from the gold standard model, providing it is a non-confounder within 10% of the gold standard. What on earth does that mean? What does that mean? Drop the least confounding variable, not the least significant variable. That's a different thing. Okay, so let's talk about what that means. And then let's see if I said any more. And then I said rerun the model without the drop V and keep dropping V sequentially using this change in estimate until only truly confounding V's remain. That's what this says. That's what this that's what this approach says. And at that point, you could stop, or you might want to do something. When you're doing this process, you're not doing anything about precision, you're just checking for confounding. So you might say, once I've finished with this process to get the best confounding model, using a shortcut backward approach, maybe I ought to look at precision. So that's what I'm doing at the end of this. Now let's look at the M Rsa example. Let's see how this works for the M Rsa example. Okay, now, here's the starting model, right? Previous hospitalization, age, gender, PAM. Those are the variables in the model. We've seen this. Okay. Now, what I'm asking in this first step of this change in estimate rule is I'm saying, can I drop, which variable, if any, can I drop that's the least confounder? But I'm only considering dropping one. That's the first step, not 2 variables, only 1 variable. Well, here's the gold standard model. Here's when I drop age. Here's when I drop gender. Here's when I drop PAMU. Okay, and you see the odds ratios for this. You've seen the same ones as before, same ones as I showed before. Now, of the 3 variables I've dropped these 3, age, gender, PM, separately. Of the 3 variables I've dropped, which one is the least confounder? Well, there's only one of them, right? There's only one variable that's not a confounder of these 3, right? When I drop it, which one is it? Gender. If I drop the others, the 10% rule, it's a confounder. So this says at the first step, I should drop gender providing it's a non-confounder. Is it a non-confounder on the 10% rule? Huh? Yeah, because it's less than 10%. And we already saw that several times now. Okay, so that's the first step of the change in estimate rule. Okay, now we've made a decision to drop this variable. What's the next step? Well, after this step, we've dropped gender. There's 2 variables left, right? Age and PAMU. Okay, so we want to see whether we can drop either one of those using the change in estimate rule. The same thing. But we're now going to the second step. Okay. So here's the second step, okay? So anyhow, I haven't done it yet. So at the first step, the BWC, a backward change in estimate approach, you should drop gender, giving the following reduced model. That's the reduced model, okay? This is not the most difficult thing I'm going to do today, but anyhow. Okay, now what I've now done is I'm showing you another table, okay? And in this table, I've got more models in here, but some of the models I've sort of darkened out. I've shaded out. You notice this model has the V's in the model are gender and PAMU. Why have I shaded that out? Because that has gender in the model, and at the first step we've dropped gender. So that's not an eligible model using this approach. Nor is this model, nor is this model, because all 3 of those models, or all 3 of the models shaded, have gender in them. I've already dropped it. Okay? So the only models that are left compared to the gold standard is the model that has age and PAMU, doesn't have gender, or PAMU without, the age and that's the one I got after I dropped gender. That's the one I got after the first step. But maybe I can drop one of these two, either dropping age and getting PAMU, or dropping PAMU and getting age. So these are and then there's the model that has nothing in the model, none of these two variables. But that's the third step. The second step says, can I drop another variable? If I can drop another variable, then maybe there's a third step. But what about, can I drop PAMU or age? In other words, I've dropped gender, but can I drop PAMU? If I drop age and I just control for PAMU, have we controlled for confounding? No, because there it says no. Okay, it's not within 10% of the gold standard. And if we drop age, can we draw? Well, it's even worse. No. Okay. So what this means is that at the second step in the change in estimate rule, we can't drop either age or PAMU. That's the second step. First step, we can drop gender. The second step, we can't drop either of the two that are remaining. That means we're done with the change in estimate rule, the backward change in estimate rule. We don't even go to a third step because we're saying we're done. We've now finished. We can't drop anymore because we need to keep both of them in because they're both confounders once we've dropped gender. That's what it says. And this is a way that we haven't done all possible subsets. All possible subsets is what we did when we had these three variables to start with. We had several models. But now we're only focusing on a subset of those models. We're not looking at the ones that are shaded. We're not even looking at them because we dropped them out when we did this step. So this is an alternative way to do this thing. It's a shortcut way of doing it. And you could also look at, given that it's either one of these two, given that we can't drop either one, this is the only model that we can compare to the gold standard, and we're back to the way we were with the all possible subsets. Those are the two models to compare, and we know we gained a little precision when we dropped gender, but we didn't gain that much, so it's debatable. Both these models give the same thing. So that's the backward change in estimate rule, okay? And that's how it works, okay? Now, you're going to have to think about this because this is an alternative way of shortcutting the process of doing all possible subsets. And it's nice because you're not doing everything that's going to maybe drive you crazy if you have 10 variables, but it might not give you it might miss some subsets that you get if you look at everything. So that's this other approach. So there are two other approaches that people sometimes use, and of the two approaches, the BWCE is often considered as another approach, except that it may not look at all possible subsets, and unless you look at precision after you get to that and get to the final model, you haven't considered precision because it's only dealing with confounding. You get this? I'm not sure if you do, but I tell you, this is the kind of thing that scares you. On the exam, whoa, right? On the midterm, there's going to be a question about this. Whether you can figure this out with some data. Okay? Oh, now you were. Okay. So anyhow, so that's basically, so basically at the second step of the BWCE approach, you can't drop either age or PMU, so the final model has both of them in there. Okay? That's it. Okay? So, and this is just a summary of the precision, or summarizing the precision, just like I said. And that's all I'm going to say about this. This other thing that's in there is not very important, so I'm going to skip that. And I'm not going to ask anything about the last two slides in here. So I want to go to the next topic, which is more complicated. Let's see. Here we go. This is the one that's maybe going to give you some, I don't know what the right word is, conniptions? You heard that expression? I'm not sure. Modeling strategy with several E's. And this is what I'm going to spend the rest of the time talking about, but I'm not going to finish this. And in fact, there's some stuff in here that I've actually put in these in this PowerPoint presentation that's on Blackboard I've actually put some material here in an appendix. I modified the original PowerPoint presentation to put some slides in an appendix because we don't have enough time to talk about that, and I'll explain a little bit about something about what's in the appendix if I get there today, and if I don't, I'll explain it next time. Okay, so now we're talking about modeling strategy when there are two or more E variables. This is more complicated, okay? So I warn you here, okay? And we're going to look at this, first by considering the M Rsa data set, but up to this point we considered the M Rsa data set, we only looked at one exposure. Now we're going to sort of hypothesize or change things around a little bit to consider, well, what would we do with that data set if two of the four variables were actually exposure variables, and the other two were C variables, which turns out to be V variables that we wanted to put in the models as potential confounders. What do we do? How do we do that? We're going to look at a general model for how you would deal with that. We're going to look at this example, and then we're going to do some other things, depending on how much time we have today. So here's, and up to this point, summary for the KKM. This is Kleinbaum, Cooper, Morgenstern. This was originally written in that book that that came out of that meeting that wasn't very good with Nathan Mantell that I mentioned. So, but this is the this is KKM with the single E. Now we're talking about several E's. So let's look at this example. I'm skipping to this slide. Okay. You find the slide. You got the right PowerPoint presentation. Are you in the room? You remember Peter Sellers, and when he was playing, was he playing the detective? Detective what? Trousseau. Okay. He would say, anybody in the room? That's what it reminded me of. Anyhow. That's not funny, but anyhow. That's what he'd said. Okay. So now let's consider this situation. Okay. Okay. Now we've got the same data set. Okay. But now I'm saying, suppose because of what we were studying and the way the investigators were looking at things, they decided that these two variables, previous hospitalization and PAMU, were exposure variables. They didn't know, they wanted to determine whether either one or both were important determinants of whether somebody got MRSA or not, and the only two variables they wanted to control for, there may have been others, but the only two variables we want to consider, at least in this analysis, is age and gender. So age and gender are the C variables, and PAMU is no longer a C, it's a second E, okay? Now, if you think about this, look at the model I've written at the bottom of the screen here, the model I've written, involving these variables. You notice I've got E1 and E2 in the model? This is a logistic model, right? I've written in logit form. I've got E1 and E2. I've got V1 and V2, right? So I've got the two E variables by themselves, and I've also added the two V variables. Now, what are these terms in here underneath it? They're product terms, okay? And the first four of them are product terms of what? They're EWs, right? E1W1, E2W1, E1W2, E2W2. What are these terms? They're product terms of each exposure with each control variable, right? It's the product term of E1, previous hospitalization with age, and then E2 with age. That's what this is. And then the next two are E1 with PAMU and E2 with PAMU. Okay, that's what I've got here. But then there's another one, another variable in the model, another term in the model. It's E1 times E2, right? Because those are the other, we have E1 and E2, why not the product? If we're talking about if we're allowing at least two-factor products, let's put the two-factor product in there. So how does this differ from the model we've considered up to this point? Well, it's got two kinds of interaction terms, right? And they're really interaction terms because both of these two sets of product terms, this kind and this one, there's only one of these, but this one and this one involve E's. Remember, if I had gender and age and I had a variable gender times age in the model, that wouldn't be a interaction term in the terms of it doesn't involve any of the E's. Okay, that would be a gender times age is a V term. It's a product of two V's. It's a V term. But these are all different product terms. Okay, so there's two kinds of interaction terms. Okay, so the problem, just for this simple situation, imagine if you had 5 of these E's and you had a lot of, you know, how more complicated it would be. But just look at this situation. So what do you do here? Well, one of the issues you have to worry about, you know, if you're following the modeling strategy, this is your starting model, right? Your starting model. Let's say we decided this is the starting model, okay? What's the next step after the variable specification stage? Well, is the model hierarchically well formulated? And the answer is yes. What's the next step? Interaction assessment, right? How do you do that? Well, one way to do that is do a big chunk test for all the interactions. It's one way to do that, okay? The problem with that, well, you could do that and find that it's either significant or not significant, but there are two kinds of interactions. So you might say, well, maybe I should consider them as two different kinds of things. And I should consider either one kind or the other kind, and I have to decide in which order to consider them. And of course, you remember the second step was interaction before confounding. So we don't look at the V1 and V2s, and we don't even look at the E1 and E2s until we decide what about these product terms. Get where I am here at this point? Okay, so how do you do that? Okay, yeah, question.
Could I know why there are 2 down 3?
Why are there
2 down 3?
2? Oh, because I made a mistake. That's why. Thank you. Should be delta 4. And this should be delta 5. Thank you. I'm going to make sure. You know, until you said that, I've been using this slide a couple of years in a row. You know, will I change it? You know? Okay, so what is this slide for? Change. For either this year or next year. That's why. That's good. Good. Thank you. Okay, so that should have been delta 4 and that should have been delta 5. Good. Is that the worst thing you're going to have to deal with today? No. Okay. So, what do you do next? Any other questions that I missed here? You know, but I missed that one. Okay. Now, I'm not going to change it here because I'll screw it up. So, now look at this. What's this? What do I say here? I say, I write at the top, it's the general EVW logistic model with several exposures. That's what I've written here. Look at this. Does this make you want to drop the course? Does this make you think you're not going to make it? You know, because you need to know about this issue about what happens if you have several exposures. Well, let's just look at this model without getting all worked up. This is a general version of the model I just showed you. Okay? Now, first of all, you notice it said logit P of X, so we know we're doing a logistic regression model, and it's got an alpha, right? That's the intercept. And you notice here are some terms. It's got a summation, and it's got betas, and it's got EI. What's that similar to? It's similar to these two terms here, right? Which has the 2 E's in there. Except in general, you may have more than 2 E's. So I've written it as a summation, or if I want to write it out in terms of all the E's, I've written it E1, E2, up to whatever number of E's I have. I'm saying EQ. There's QE's. Okay? You know, as soon as you start as soon as you try to write something general, you have to worry about notation, and you have to make it sort of work in some way. And so that's what this is. There are Q of these E's. Okay? And then the next set of these variables in this thing are the V's. Okay, how many V's were there? 2. How many V's are here? P sub 1. In our example, P sub 1 is 2. There are 2 V's. So I've now written a general way of writing the V's. Okay, and then the next thing I have is EW terms. And I actually got a double sum, which makes it, you know, for those who are mathematically, I don't know, worried, I don't know what the right word is, that may scare you, the double. The reason why you have double is because you have E's that are being multiplied by V's, and then when you multiply by V's, they become W's. But in any case, that means you have different kinds of E's and different EW's, and this set of terms that is written over here is essentially a way of writing these four product terms, E1W1, E2W1, E1W2, E2W2. That's what that is. It's not that bad, really, if you think about it. You just have to work with it. And this is this is a product of the E's, and it's only two-way products. It could get worse. You could have three-way products. So I'm trying to keep it simple. If I had three-way products, it's not like I couldn't do it. So I'd be asking for problems, like I mentioned about multicollinearity, which is something we're going to talk about later. But this is a simple but a general way of writing this model that I illustrated, using this. Okay? So this is the general form of the model. Okay? And these only have E terms in there, right? So the general way to write the model. Okay? So now the question is whether you have the example or you have the general model, what do? How do you go about the process of getting a best model? Well, again, you got several E's, and you got two different kinds of interactions, okay? So how do you go about the process? Do you consider one kind of interaction before you consider another kind of interaction? Well, it seems to make sense you should consider interaction before confounding, but do you really? Now, here's the thing, and I'm going to talk about this. This is where it starts to get a little complicated, okay? But we're going to continue with this thing for a while, okay? Now, first of all, here are two ways you can go about the strategy for this model. It's not the only two ways. To me, it's the two ways that make most sense. These are like the I had guidelines when there was one E. These are the guidelines when there's more than one E for how to go about the process. And it's not the only thing. There are other ways, but this is a sensible way of doing this thing. Now, look at the guidelines. The first step there's two alternatives. First step, alternative one, is variable specification to determine the E's, V's, and W's. Okay, you notice that's the first step for alternative one. It's also the first step for alternative two. So you start out the same way. Start out with your model in terms of what makes sense to you in the initial model. The second thing says interaction assessment involving EW's. And the second thing here says interaction assessment involving EW's. So you see alternative one and alternative two start out, the first two steps are exactly the same. See that? Same thing. Now you notice what the second step says, that when you assess interaction, you're going to first consider the EW's before you consider EE's. Isn't that what it says? I mean, EW's come first. That's what it says. It says it alternative one and alternative two. So what I'm saying, both alternatives have the same first two steps, but differs in step 3 and 4. Okay? That's what they differ. Now, one thing I should say, both of them have EW before EE is assessed. Both of these alternatives assess EWs before EEs, but there is a difference. Can you see the difference? The first one assesses EE right after EW. The second one doesn't assess EE until you consider the V's. That's the difference between the two. Okay? And it's sort of 6 of one or half, I don't know, 6 of one or half a dozen of the other. I don't know what the right expression is. But it's sort of like either one of them sort of makes sense in a way. The first one says, alternative one says, consider interaction among the V variables. Or the first one really says consider interaction before you consider the confounding it entirely. Isn't that what the first one says? Consider interaction, do this one first, this one second, but don't start dealing with the V's until you deal with interaction. Isn't that what the first one says? It gives you an order, but but this one doesn't say that. It says consider interaction with the V's, but don't consider interaction with the E's until you consider confounding with the V's. See what that's? So this alternative 2 is a little different. It says, once you consider interaction with the V's or the EW's, then look at confounding and precision with the V's, and don't touch the interaction with the E's or the E's until you've dealt with the V's. That's what this is saying. Now, either one of these makes sense in some way, but let's go. Now, as again, both of these alternatives say EW comes before EE. That's what I'm saying. EW. Now, an alternative approach, which is not listed here, might be alternative 3, says look at EE before you look at EW. That's what it says. But I don't recommend you do this. Okay? Even though there's nothing that you can't do in this, just about nothing, you could do this, but there's a reason why I recommend it, and you could take it or leave it. But, and I don't know, you think you'll take it because, but anyhow, so what I'm saying is, which do you do? Do you do EW before EE, or do you do EEs before EWs? And that's what I'm asking here. Which to check first, EWs or EEs? Well, look at the bottom of the next screen here. The bottom, I'm going to the next screen. Done a little bit more on the next screen, and look at the next screen. Alternative 3, where the EEs are done before the EW, sort of contrasts with what we did when we only had one E. When we only had one E, we looked at the EWs, then we looked at the V, and then we looked at E. Okay? We didn't touch anything having to do with exposure until we dealt with the variables that we're worried about controlling for. That's what that's what the single E strategy does. We didn't touch, but alternative 3 doesn't do that. Alternative 3 allows you to consider the EE before you've, it allows you to consider the EE in a wrong order. This is what I'm sort of saying here. Let's see what I said. Alternative 1, interaction before confounding. Alternative 2, confounding and precision before EE and E. But both of them, particularly alternative 2, doesn't let you touch the E's until the end. That's sort of like what we did when we had a single exposure. We didn't touch E. We worked with the V's and the EVs before we dealt with the V's. So that's sort of my reasoning for saying, alternative 3, starting with the EEs doesn't make sense. Okay? Although it doesn't mean that nobody can, but this is what I'm working with, alternative 1 or alternative 2. Now, where do we go from here? Well, we now say, let's look at these models. Okay, let's look at these models and let's see what we do. Now, here's the model. Okay, now, suppose we say we're going to use alternative 1. Let me see if I can. We're going to use alternative 1. Okay. What does alternative 1 say? Just to go review that. This is the model we're starting off with. What does alternative 1 say? Go back to this. It says, where it is. It says, first, after the variable specification, first assess EWs, and then after you do that, assess EEs. Do it in that step order. Okay. Now, what I'm saying is, suppose you do that, you do alternative 1. And suppose after you do alternative 1, no guarantees, but suppose after you do, which is steps 2 and 3 for alternative 1, suppose you find that both interactions, both EWs and the EE term drop out. Suppose you find no interaction when you assess interaction first, for EWs and then an E. This is your model after that. Is that correct? If there's no interaction, I'm dropping these 5 terms. Recognizing this should have been a 4 and this should have been a 5, but I'm dropping these terms because I'm saying, suppose I found there's no interaction. This is the model left after I assess interaction. So I'm now ready to go to, if I go back to the step process, I'm now ready to go to, I'm doing alternative 1. So I'm looking at confounding followed by precision. That's what I'm doing now. I'm at this step. Okay? With me? I don't know, but I'm at this step. Okay, and this is, you have to think about this. It's not that easy to think about it, but okay, so what do we do next? Well, what we want to do is we want to decide whether we need a control for either V1 or V2 or neither, comparing to just using this model. As the gold standard model is the one you now see. We've gotten rid of the interaction terms. right? This is the gold standard model. It only involves previous hospitalization, PAMU, age, and gender. Okay, so how do we deal with confounding with this thing? Well, there's a couple of ways to think about how to do that, but this is a way that a lot of people like to do. Okay, now here's what I've done. Here's what I've done. I'm trying to talk about how to consider confounding followed by precision for this situation where you're now left with this model and the two V's are age and gender. Should we drop age or gender or both? Okay. Now, one way to do that is to say, well, look, we have two E's. Okay. How do we deal with these two E's and deciding about it? It gets confusing if we consider one separately from the other. Why don't we consider the fact that the both E's are we're worried about their joint effect on the outcome. So what if we consider the following? Joint effect. We compare the two E's. We look at comparing when somebody has a 1-1 on the two E's versus somebody who has a 0-0 on the two E's. What does that mean? E1 equal 1, E2 equal 1 versus E1 equals 0 and E2 equals 0. What does that mean? What are we essentially doing? Well, we are considering how the two E's jointly work together, and what are we essentially doing? We're comparing somebody who's high versus somebody who is low, right? Or one who is yes versus no. In a sense, that makes sense because that's the most extreme situation. I mean, we could also consider 1-1 versus 0-1, or 1-0 versus 0-1 or something like that. But this is the most extreme situation. So if we want to assess confounding, this is just a way to do it, but it's a sensible way to do it. It's to say, well, why don't we do this by looking at this situation? We'll say, if we find confounding when we're comparing high to low, then we're going to decide that we need a control for one or both of these variables, and if we don't find confounding, we'll drop one of them, or both of them. Okay. Now, if you look at this, this is a little more complicated. Isn't it more complicated? It's a little more complicated. Now, suppose we're comparing E1 and E2 equal 1 versus E1 and E2 equals 0. What is the odds ratio? Isn't this the formula for the odds? If you think about the general formula for the odds ratio that you learned and reviewed in the first couple of classes, when there's no interaction, so the odds ratio only involves the exposure variables. The formula for the odds ratio, it's beta 1 times the difference between the corresponding values of the E1s plus beta 2 times the difference between the corresponding values of the E2s. And if E1 star is 1 and E1 is 0, I should have maybe written this as star, but it corresponds to X star, and E2 star is 1 and E2 is 0, then this is 1 minus 0 and this is 1 minus 0. So what do you get? You get the odds ratio has the formula E to the beta 1 plus beta 2. So what I'm saying here, now again, this is complicated a little bit. Can even get more complicated. This says that if I decided I wanted to compare high to low, and that's the way I'm going to assess confounding, I'm now focusing on this odds ratio that I want to see whether it changes meaningfully depending upon whether I control for either age or gender or both, or keep both of them in there. So I've changed the problem from two E's to which might give me two odds ratios, 2e to the betas, to a problem with one odds ratio. And I've made an odds ratio that makes sense. High versus low. It makes sort of sense. So here I have it now. Now, what I would do is I would compute this odds ratio for when I control for age and gender, when I control for just age and not gender, just gender without age, and I control for either. I'd be getting 4 odds ratios. 4 odds ratios. You follow? I'm not sure if you follow this. Okay, I could be getting 4 odds ratio, and the gold standard odds ratio is the one that you get when you fit the model, and you fit the model and use beta 1 hat and beta 2 hat for the model that contains both of them in there. And then the other models are models that only has age or only has gender or has neither. So what do you do with this? This is a table of odds ratios. It's a table of odds ratios. Now, if you wanted to assess from this table whether you can drop a variable and maybe you're still controlling for confounding, what would you do? Well, you would look at each one of these three things and see whether they're within 10% of the gold standard odds, just like we did before. But now we've changed the problem from having two E's to really one odds ratio. Yeah, Nicole. I know a few names. Yeah.
So could you have done the same assessment values of E and held them constant throughout every model as well?
The V's?
The E's. Like if I wanted to do E.
Well, remember, the E's are 0, 1 variables to begin with. So I only have, they could be continuous variables. It makes it more complicated. Okay. But in this case, the E's are 0, 1 variables. So I can only do 1, 1 versus 0, 0, 1, 0 versus 0, 1. And I could do more of these. I could not just restrict myself to focusing on 1, 1 versus 0, 0. I can do this analysis and have a bigger table to consider. But I might say any of these other tables isn't looking at confounding in the bigger sense that I'm with 1, 1 versus 0. But I could do it. It's just more trouble. Okay? It's not that you can't do it. I'm trying to make it as simple as possible to explain how you might do this. Okay, so now, let's look at the next slide and see what the next slide says. What does the next slide say? Look at this, all the bunch of stuff, but look what here. This red stuff in the next to the bottom bit of information. What have I done? I've sort of circled the ORAG and I've circled the ORG. And I've said the ORG is within 10% of the ORAG. And I haven't circled the other two, so what I'm saying is, of these other models, these are other models. This is one where I drop gender, this is when I drop age. Of these other models, this model, when I drop age and keep gender in the model, gives me the same answer as the gold standard odds ratio. And the other ones don't. Okay? And what this means is, again, this is what I said, this is a little complicated. What this means is that if you want to consider an alternative model to the gold standard model, an alternative model is to drop age and keep gender. Those are the only two who are eligible to be dropped, age and gender. Because you already got PAMU and previous hospitalization in the model. They're the two E's. So the only two you can do, and if you drop age, you wind up controlling for confounding. If you drop gender, you don't control for confounding. This is what this is meant to do. This is the only one that controls. You might get something different, but I'm saying suppose you get this. Okay. Now, if you get this, if this is what you wind up getting, this is the confounding assessment. This says you now have two models to compare: the gold standard model and the one that drops age. They both control for confounding. If you use this E11 versus E00 way of doing it, they both control for confounding. Okay. Which of the two models are you going to allow? Which of the two models are you going to actually consider as the best model? Well, none of these other models are now competitive anymore. They're out. It's only these two models. What do? I've considered confounding. What's the next step in the process? Precision. So I look at the confidence interval around this odds ratio and the confidence interval around this odds ratio, and I compare the two. And if I gain precision by dropping age, and I gain a lot of precision, then I'm going to drop age. And if I don't, I might use the gold standard model. That's the process. That's the process for dealing with alternative one. Okay. It's not alternative two, but that's a way of dealing with alternative one. Now, you're going to say to yourself, oh, I didn't do a whole bunch of other things I could have done, but I'm trying to make this as simple as possible to show you how it could be done. See if I said anything else. Okay, now, I'm now saying, okay, that's alternative one. I'm showing you how you could work with alternative one to come up with a final model. Okay. Now, let's talk about alternative two. Whoa, that's alternative two, if you remember, deals with the variable specification, and then the second thing you do is the EWs, but you don't do the EE until you've dealt with the Vs. So let's suppose that's what alternative two says. So suppose there's no interaction. This is the starting model, same starting model as we did before. It involves the two E's age and gender, these 4 EW terms and an E1, E2 term. Now, alternative 2 says, well, after you've started with this model, the next thing you do is you test for the EW terms. That's what you do. You test for the EW terms. And I'm saying, suppose there's no interaction involving the EWs. So suppose step 2, got to make it simpler than it could be. Suppose no interaction involving the EWs. What would that mean? You see this model that I've written down here? This is the model after this step, given what I've supposed. Why is this the model? What have I dropped out of the model? All the EWs. Why? Because I've said they're non-significant. I mean, they may or may not be. Let's suppose that they are. I can drop them. This is a simpler model. How does this differ from the previous model that we dealt with when we were looking at alternative 1? Well, there's this thing here, this elephant in the room. I don't know what you call it, the E1 times E2. That's in the model also, because we're not testing for this. I mean, this third step says don't test for this. Test for the EWs, but don't deal with the E1, E2 until you dealt with the Vs. See that? That's what alternative 2 says. And it's reasonable in the sense it says don't touch the E's until you deal with the V's. That's what it's sort of saying. Okay. Now let's talk about what do we do next? Well, we can assess confounding and precision involving the V's, keeping E1, E2, and E1 times E2 in the model. That's what alternative 2 says. And so the odds ratio formula for now alternative 2, the odds ratio formula now is more complicated. The odds ratio formula involves not only this coefficient and this coefficient, but it also involves this one, right? Which I should have called delta 5, but it's still there, it's delta 4, okay? Because the odds ratio involves E's. In terms of how you get an odds ratio, it involves something having to do with the E's in how you compute the odds ratio. So let's look at the next slide. Suppose I do the same thing as I did previously with alternative 1. You see how this is getting complicated? And some of you are saying, yeah, I'm dying here. Are you? You might be. I don't know. I'm trying to, I don't know. Anyhow, suppose we do the same thing. Suppose we go high versus low. Okay? High versus low. But we're using this model now, which has this extra term in there. Okay? If it's high versus low, and I get the odds ratio for high versus low, this is the formula for the odds ratio. It's different from the formula we had before. How is it different? What's different about the previous that we have consider the previous formula? It has another term in there. It has the delta term, the coefficient of the product term involving the E's, right? That's how it differs. But it is an odds ratio expression. So if we want to assess confounding, now what we're doing is we're saying we're keeping the EE in there, but we want to assess confounding before we even evaluate the EE term. And what we're going to do is we're going to basically do the same thing as we did before. We're going to get a table that considers this formula for the odds ratio and compare the situation with these 4 different situations where the gold standard, dropping gender, dropping age, or dropping both. And I've just decided I could have done it differently, but I'm basically saying suppose it turns out that just as it happened for alternative 1, for alternative 2, it turns out the only model that controls for confounding is the one that drops age, just like it did for alternative 1. So these are the only 2 models, the gold standard and the one that drops age. If you're doing this, how am I going to do this? I'm going to get beta 1 hat, beta 2 hat, delta hat, and I'm going to compute the odds ratios for these different models. I'm not computing it all for you. I'm just showing that if I did, it would take me longer. But anyhow, what we're saying is that these 2 models, just like with alternative 1, if we did this and we wound up getting this example, would be the same 2 models that are competitive for the best model. And then we compare the confidence intervals. And if we found that we gain precision, that's why I put the star in there, if we gain precision by dropping age, then that would be the right model. That would be the best model. So that's how you would do it for alternative 2. So I've shown you, without doing numerical example, how you can work with both alternative 1 and alternative 2. In the simplest situation, you could have 2 exposures and only 2 V variables. What if you have 5 exposures and 4 V variables? And what if you have a question like that on the midterm? You know, right? So you're starting to, but you got to understand this. And this example with actual output is in the book. In the textbook, in chapter 8, when I talk about this, I actually put in the output for this. So I actually worked through numerically this. So you should really read that. You should really see that if you want to get more specific on this thing. So there you go with that, okay? So now, but we're not done with this. I haven't done with this model. All I've done is I've dealt with confounding, okay? But I haven't done, if the alternative 2, I haven't dealt with the EE term yet, right? With alternative 2, the 4th step is consider what happens with the EE terms or any EE terms. So after this step, if it turns out that I was able to drop age and keep gender, this would be my model after I assess confounding followed by precision. And this model has E1, E2, V2, because I've dropped age, and it now has E1 times E2. What do I do next? What do I do next? For this step, what would you do? Test for the E1, E2. That's the next step, right? If it's significant, you're going to leave it in. If it's not significant, you're going to drop it, right? That's the next step. I think that's what I say. I hope I say that. Okay, assess EEs and E's for model after step 3. Okay, that's what the next set of steps is 4 and 5. You first assess EE, and then you see what happens after you get that, and you assess whether you... Now, let me ask you this. Suppose when you do this, you find that E1 times E2 is significant. What's the next step after that? You're done. That's what Emily said, right? You're done, right? Because you have to keep E1 and E2 because they're, subsets. They're lower order components of E1 times E2. And you also decided you had to keep V2 because of what you did in the confounding assessment. So you're done. Okay? Get that? So, but now, what happens if E1 and E2 are, not significant? What do you do? Let's see. Okay? So that's what you do. Now let's say where we go. Okay, now, so suppose, let's consider this. Suppose E1 times E2 is not significant, so the reduced model looks like this. I got rid of all the product terms somehow. I did it either alternative 1 or alternative 2. Suppose the model doesn't have any product terms. It just has the 2 E's and just has gender in there. What do I do here? How do I decide what to do at this point? Okay. Well, what would you do? There's a couple of alternatives you have. One alternative you stop. This is my model. I have both of them in there. And I'm going to have to do something about what the effect of E1 or E2 is or what the joint effect is or something like that. That's one thing I could do. Another thing I could do, an alternative to that, is do what? Well, I got E1 and E2. Do I need them both in there? Do I only need one? Was one good enough? Is once I have one in there, do I need the other? Which one of the two is more important? So that's what I'd want to consider doing here. So there's several alternatives, is what I'm saying, to how to consider this, okay? Okay. So, and I'm going to do that in a second. Not in a second. I'm going to do that in a few minutes. But now I'm going to get to this thing, how you deal with this thing and some of the alternatives, okay? Before I do that, look at the model I've written here. Model I've written here. This is not, well, this is the M Rsa data set, but what have I done here on this slide? I've said basically, I don't know anything about any of these variables that I'm dealing with. I don't know anything about them. I don't know anything about age and gender and its relationship to M Rsa either. They're all exposure variables. This is almost like hypothesis generating. I'm at the start of research on this thing, and I'm treating them all as exposure variables. So they're all E's. So this is my starting model. See that? Isn't that different from the two models, the previous things we've done? Very different. Okay, what do we do here? Well, you notice there are no V's in the model, right? There are no V's in the model at all. So if we're talking about the modeling strategy and there are no V's, okay, do you have to worry about confounding? You have to worry about confounding? Well, it's debatable to some extent. You might say, I might have to worry about some confounding of one E with another E, but I don't know enough about these E's to even suggest that. So you might say the whole business of the modeling strategy with the confounding and the precision for the V's, I no longer have to consider that. So what might you do instead if you wanted to consider what to do here? Give me a suggestion. Anybody give me a suggestion? You notice the model has the 4 E's and it has all possible two-way products. What might you do first? Test for interaction, right? That's the thing you might do. And do a chunk test for interaction, and if it's whether it's significant or not significant, you'd probably go backwards and decide whether you can drop any or all of the interaction terms. And any interaction terms you can't drop, you're going to have to keep the lower order terms in the model. If you drop all the interaction terms, then you're left with just E1, E2, E3, and E4, right? So that says, okay, there's no V's. Let's do, and this is what I'm describing is what most people do when they're doing statistical analysis and they're treating all the variables like they're the same thing. And that's what you sort of learn in some statistics courses. I don't know whether that's, a lot of statistics courses or statistics teachers, when they talk about regression, they talk about just doing backward elimination with the interaction first and then the main effect variables next, but just not worry about confounding because they're all competing equally. I'm not considering an E variable different from a question.
So is this the same idea as a predictive?
Well, it's not really necessarily a predictive model because once you get to the final model, let's say you get rid of the product terms and you get down to the 4 E's, or let's say you even get down to 2 of the E's, okay? You still want to know which one of these E's is important and how they predict what the association is. So it's not necessarily a predictive model. You can still be talking about the association and the joint association of 2 or more E's or not. So you can still be talking, you can always talk about a predictive model, but I'm sort of trying to treat this whole modeling strategy as if you're still in the position of etiology, okay? So I'm watching the clock because we only have a few more things to go. So how do you do this, okay? How do you do this? And I'm going to continue this next time, but I just want to say a few things more. Well, first of all, I've already said what I said. First, after you specify this model, the next step is interaction assessment, okay? And then if you were trying to follow the modeling strategy, the next step after that would be confounding precision assessment, except there are no V's in the model, what I'm saying. If there are no V's in the model, should you do confounding or precision assessment? And it's sort of debatable to some extent. It's sort of debatable, but I don't like it. Just because I don't like it doesn't mean I'm right. But I'm just saying it's so debatable that to describe how debatable it is, I actually spent a lot of time writing what's now in Appendix 1 to talk how debatable it is, and I don't got time to talk about it. And you're not going to be asked any questions about it either in terms of the midterm. But if you're interested in it, you should try to have a meeting with me or get a group together and talk about this. Look at those slides that are in Appendix 1. But basically what I'm saying is you can skip this step if you don't have any V's, what I'm saying. Now, it's debatable, and the way it's debatable, I describe in Appendix 1, but that's what most people do. They skip the step. That's what most statisticians do, okay? Now, and then you do exposure assessment. Now, I haven't really talked about this per se. This next slide basically says, do a chunk test. If you're skipping the confounding statement, you do a chunk test for no interaction, followed by backwards elimination involving only product terms, and you keep in the model any E that are components of significant product terms. So if you find that these 2 product terms are significant, you have to keep E1, E2, and E3 in the model, but you might drop E4, in terms of the hierarchy principle. Do you understand what I'm saying? If these two are significant, you have to keep these three, but you can drop this one. If none of them are significant, anything goes. You can have all four, you can have some subset of them in there. Okay? And what I'm going to start doing next time is talk about not the confounding, that's Appendix 1. I'm going to talk about, you see number 4, exposure assessment, several options. And I'm going to talk about, that's when I'm going to start next time, talking about the several options. And the several options are described in these next few slides. Okay? So that's where we are. Did you follow this? How many are totally lost? Raise your hand. Are you totally lost? Are you partially lost? Are you partially okay? I don't know. I don't know. Do we take a vote on this thing? This is the most complicated thing we've done so far. Okay? Okay? So I'll see you on Thursday. Okay? Talk some more about this.